Hi everyone, and welcome back to another AP Calculus video. Today we're going to introduce you to polar functions. Now this video does assume that you have at least heard of polar functions and been exposed to them. But let's review just a few things about how they work and what the deal is with this r and this theta. Now let's understand that there are two ways to express a location of a point in space. René Descartes developed his rectangular XY Cartesian system, and when you develop something, you get the luxury of having it named after you. So that's why we refer to it as a Cartesian coordinate system. And it's called a rectangular system because the pattern that we use to make the points when we go over X and up Y creates this rectangular pattern. So that's one way to find things in space. And up until you learned about polar equations, it's the only way you've ever graphed something in space is through a Cartesian or rectangular plane. Now, a polar coordinate system allows us to plot things in that same, we can plot the same point, but it's a different set of instructions. So instead of giving us an X and a Y in the Cartesian plane and saying go left or right and then up or down, now the polar system allows us to graph things by sweeping around at a certain angle and landing in a certain direction and then moving outward by r radiuses. So consider the middle, the origin, to be the center of a circle, and the polar graph gives us concentric circles, so circles that all have the same center, and r represents how many circles are we going to jump outward. Theta tells us how many degrees or how many radians we rotate around, and then r is how many rings we're going to move out. And the polar graphing system looks like this, where here's our, you can see the different radiuses. So r is 1, 2, 3, and then you have your angles. So this is, it's a lot like the unit circle in how we deal with things. And when we graph a polar equation, what's important to understand is that no longer are you moving left, right, up, and down, but instead you are sweeping around and moving out. And when we plot some points, we plot them usually, we're so used to seeing X and Y and going over X and up Y. And here, this set of ordered pairs right here, this would be what we call r, and this is what we call theta. And we actually, when we plot, I prefer to deal with theta first. And what theta does is theta tells me how far to rotate around, and it's always an angle in standard position. So if we're going to plot 3 pi over 4, I'm going to come down here to my polar grid system, and I'm going to go to where pi over 4 exists on the graph, and pi over 4 is right here. So this is kind of the line that we're going to move across. Now it's called a polar system because these lines that run through the angles, those are called your poles. So you have the rings that are r and then the poles for each angle. And you don't have to stick with unit circle angles like pi over 6, pi over 3, pi over 4. Every single angle will have its own pole. We just tend to show and count by the standard unit circle angles. So I'm going to rotate up pi over 4 and move out 3 rings. So this would be the point 3 pi over 4. It's important to recognize that if we have a negative r value, so for example, if I wanted to plot the point negative 3 pi over 4, I would still rotate to the pi over 4 pole, but if r is negative, I would just go backwards, 1, 2, 3. So this would be the point negative 3 pi over 4. In the polar graphing system, different points can have multiple names. Like for example, this point that I just plotted, negative 3 pi over 4, you could also call it positive 5 pi over 4. Because remember, this is how it works. So we go pi over 4, this is 3 pi over 4, and this would be 5 pi over 4. So if we change the angle and rotate all the way around to 5 pi over 4 and then move out 3 rings toward the angle, then we'd have a positive r and a slightly different angle. So the positive r value means we're moving out towards the angle. A negative r means we rotate that angle and then move away from it. So it's a directional sign thing. But the important thing to remember is that in the polar system, the same point can have multiple names. Not true in the Cartesian system. We also want to recognize that when we graph equations, they usually are of the form r equals, and you'll have some function r equals some function of theta. And we're going to see that here in just a few minutes. But we also have functions like when you have a vertical or a horizontal line, we can have singular valued functions here in the polar system. So r equals 3 and theta equals some angle also show up in our polar system. And when we graph something like r equals 3, what that means is that it's not tied to an angle. So if I'm going to graph r equals 3, what that is it's the set of all angles along this r equals 3. Well, r equals 3 everywhere along this ring. So in the polar system, when you have a graph r equals 3, it creates a circle. So it's all of these points and everything in between. And it's important to note that r equals a number is just a circle with a radius of that number. So let's make a note of that. R equals 3 is just a circle with a radius of 3. Now the Cartesian equation would look like this: x squared plus y squared equals 3 squared. It's a circle centered at 0, 0 with a radius of 3, or it would just be x squared plus y squared equals 9. Now, theta equals pi over 3, we want to think about it in the same way. It's the set of all angles where theta is pi over 3, regardless of what r is. So when we graph an equation of theta equals pi over 3, if we go to our polar system here, here's pi over 3, here's pi over 3, here's pi over 3, here's pi over 3. Now, you create this line here all the way anytime where theta is pi over 3. Now you also have to understand that because of the way the polar system works, if you have a negative r with a pi over 3, that simply means you're going to rotate to pi over 3 but then move backwards. So we actually have a line that extends all the way, and you have this line through the angle pi over 3. So we have circles and lines when we have just singular variables. So this is a line through pi over 3, which, by the way, in Cartesian format, this line would have a certain slope, and the slope is the tangent of the angle. So here my slope is square root of 3. So the equation in Cartesian would just be square root of 3x. It's just a line with a slope of square root of 3. So remember, tangent is y over x. It's rise over run. Well, y over x, that's my tangent. That's my rise over my run in my Cartesian format. So the tangent of the angle is the slope of that line. So there's a little connection. And again, this is something that if you are one of my students, you would have been exposed to in pre-calc. Whether you remember that or not is another story. But I know that you have seen it at some point in your life. So now that we kind of have a handle on how these polar graphs work, let's take a look at what goes on when we graph a polar equation. Now, we want to understand that when we graph, what happens is our calculator, or in this case Desmos, plots values, and I have the function set here to go from 0 to some value of a, and a will extend all the way to 2 pi. So watch what happens. When I click play on this and allow a to kind of run through all of its values, you'll see that it just kind of sweeps around and it plots these shapes. And so as it goes along, it's saying, okay, as I move through the angles, r changes because r is some function of my theta. So when theta is pi over 2, r is the length of that little green line that you see kind of rotating through. And r changes based on the value of the angle. So you have 2 plus something. So when the cosine is negative, like that is in quadrant 2 and 3, you'll see that r gets a lot shorter because it's 2 plus 2 times some negative value. So it creates this cool shape, and this is a specific kind of shape called a cardioid. We have a couple different types of graphs we're going to take a look at, but this is a really common one. And our goal in this chapter is to be able to find a couple of things involving basically 2 types of things, well, 3 types of things. We're going to discover what the derivative is so that we can find equations of tangent lines. And then we want to be able to find the area inside of a polar curve. And then we also want to be able to find the length of a polar curve. So those are the 3 things that we're going to be doing over the next couple of days and in these videos. Now, on a regular basis, you're going to be asked to look at the graph of a polar function. So we need to learn how to we need to learn how to graph these polar functions in our calculator so that we're able to view them and make some decisions about them as we kind of learn how they operate. So one of the things I'm going to do is I'm going to make sure that I'm going to change my mode. And I'm going to put my mode into polar function. So polar function allows me to, when I go to my y equals screen, see r equals. And you'll see that I do have some, I'm going to clear everything out. And I'm going to go ahead and start typing in this function, 1 minus cosine theta. Now what I would recommend to you is if you have a graphing calculator, go ahead and pause right now and get that graphing calculator out, put it into polar mode, and follow along here. I'm going to keep going, and I'm going to just hit zoom 6 and see what happens. That's kind of my general way of things. And when I look at this, it's kind of hard to see, and maybe I need to set my window. It looks like maybe 2 to -2 or 3 to -3 might be appropriate. So I'm going to go to my window, theta min, theta max. This tells me what values of theta. So kind of like a parametric equation, it tells me where to go. And usually it goes 0 to 2 pi. So 6.28, that's your 2 pi value. Now your theta step, you want to make sure that that stays small. If ever it's too big, then what happens is you get kind of this jolty, straight lined with sharp edges kind of function. Remember, the theta step or the x step or the t step tells your calculator the intervals to what to change t by as it's plotting its points. So how far away is the next point? And if it's too big, then the point's too far away. It connects it with a straight line. So that's kind of the problem with that. So we're going to keep it small. We're not going to worry about it. But I'm going to go -3 to 3 for both of these. Oops, -3 to 3. And then I'll hit graph again. And it'll zoom me in. And I see I've got this cool looking function. And it's kind of skewed though because my rectangular screen. So one of the things, once I get it in my window to where I like it, I'm going to hit zoom 5, and what zoom 5 does is it kind of squares up my window, and now I can see that this function actually, this is what it actually looks like. It's not that, elongated thing. It's this nice round. So this is how we graph these polar functions in our calculator. So again, change the mode to polar, go to y equals, make sure that you adjust your window as you go. We could probably zoom in a little bit further on this one, but I think we're okay for now. You can see that the zoom square does change your x values to give you a squared off look, and it accounts for the rectangular shape of your graphing calculator screen. Now, in addition to be able to graph a polar equation in polar form, we want to understand the relationship between polar equations and rectangular equations. So we have a couple conversions here, and what we want to understand is that this simply comes from the relationship in a circle where if we're going to graph, and we have a circle here, and we have this angle theta, where r is the radius, and that's how we get these graphs. To find the x-coordinate and the y-coordinate, it has to do with trigonometry within this right angle inside of my circle. And so to get the x value, I'm simply doing, r cosine theta. To get the y value, I'm getting r sine theta, and that has to do with the fact that, the cosine of theta is simply x over r, and the sine of theta is y over r. So that has to do with those trigonometric ratios. And just as a little reminder, tangent of theta is y over x. So there you go. But this is how polar functions relate, and this shouldn't be any sort of new information if you've had pre-calculus. This is pretty easy to understand. So these are the conversions. To convert to the xy coordinates, we simply use r cosine theta, r sine theta. We also want to note this relationship with the Pythagorean identity. So I'll zoom out here. We've got a right triangle trigonometry happening. So our Pythagorean theorem tells us r squared equals x squared plus y squared. To solve for r, we would use our square root. And then tangent of theta is y over x. And notice when it says theta equals some angle, it will always be a line through the origin with a slope of tangent of theta. That's important to note because that will come back around. So if I wanted to convert r equals 4 sine theta into a Cartesian equation, my first step, and let's get ourselves a little bit of room here. My first step is going to be to replace any thetas. So coming back up here, I have a sine theta. So I'm going to remember that y equals r sine theta. So to replace sine theta, I'm going to replace it with y over r. So I'm going to get sine theta alone. Whoops, y over r, not y over y. So this is what I replaced sine theta with. So this is my equation thus far. R equals 4 times y over r. Now my next job is to try to get r squareds, because I know that r squared can be replaced by x squared plus y squared. So I'm going to multiply both sides by r. So this gives us r squared equals 4y. Now remember, the whole goal of converting to a Cartesian equation is to get rid of r and theta and replace it with an equivalent version using x and y. So now I'm going to remember that r squared is simply x squared plus y squared. So this would create equals 4y. Probably some sort of, I would guess, an ellipse or some sort of shape here. I don't know. I'd have to kind of look at it. I'll be honest. I don't have my polar equations memorized, so to know what 4 sine theta is off the top of my head, I'd have to kind of look at it. But here's our, general form of some sort of probably some sort of conic section of some type. And again, not something I have memorized. So that's how we convert to a Cartesian graph. And this is just meant to be an introduction to how these polar equations work. In later videos, we're going to actually do a little bit of calculus with them. So practice, get comfortable, understand how they work. And one thing I will note here is that as we move forward in the next video, just kind of as a sneak peek, we're going to start representing and understanding that we can represent polar equations, or we can represent equations as a set of parametric polar equations. So if x is our cosine theta and y is our sine theta, then my parametric version of this would look like this. I would have r cosine theta, comma, r sine theta. And all of a sudden now I've got these parametric equations, or vectors if you will. It's all kind of the same, they're all related, and we treat them the same and do the calculus the same. But instead of x's and y's and t's, now I have r's and thetas. So really it's all related, and parametric equations kind of permeate through this chapter. We've got general parametrics, we've got vectors as parametrics, and now we have polar functions that we can represent as a pair of parametric equations. So get comfortable with them, keep practicing. You can do this. You've got this.